Today we're going to look at graphs of motion. The motion of any object can be portrayed on a graph. For the graphs of motion for vectors, we will be looking at displacement time graphs, velocity time graphs, acceleration time graphs. We are going to be looking at what information we can get from those graphs and what the shape of those graphs look like and what they mean for us. Remember, a graph always consists of a y-axis, which is where we put the dependent variables. The x-axis is always the independent variables, and with equations of motion of a graph, motion of an object, time is always the independent variable. We are going to look at a summary of the shape of the graph. So the first thing is when we have constant velocity, the displacement time graph is always a straight line. That straight line may have a positive gradient, as shown here, or it may have a negative gradient. It all depends on whether it's going in the positive direction or the negative direction. In both cases, it doesn't matter, equal amounts of displacement is covered in equal time periods. It's a uniform velocity, it's not changing. As a result, the velocity time graph is a horizontal straight line. In the positive direction, it's above the origin, as shown here. In the negative direction, it's below it. What it means, though, is there's no acceleration. So your acceleration time graph can be drawn on the x-axis. Acceleration is 0. If we have constant positive acceleration, we now see that my graph starts to curve, or displacement. That tells me in equal time frames, we get smaller and smaller. Well, we get bigger and bigger, I apologize, bigger and bigger amounts, distances covered, okay? Those aren't to scale at all. It also means that my velocity is changing by the same rate, so my velocity is a straight line with a gradient that's not equal to 0. And my acceleration, in this case, I told you it was positive, horizontal to the time axis. Constant negative acceleration usually means deceleration. And now you'll see that my curve starts to get smaller and smaller. So the angle, the gradient of the graph is getting smaller and smaller. Eventually, though, this should get to a straight line. That just tells me it's stopped. I now have a negative gradient to my velocity. All right, still a straight line. And my acceleration goes below the time axis because it's negative. If we look at each of these sets of motion in turn, 1, the graph for an object at constant velocity in a positive direction, displacement constantly changes, it's moving. Velocity is constant, I said that. Acceleration is 0. So, the displacement time graph, straight line. Going at it has a gradient. Why? Because it's moving away. It's not staying in one place. That positive gradient represents the velocity. That velocity is positive, it's above the ground, above 0. That gradient comes from here. It's positive. This gradient is 0, so it gives me 0 acceleration. There's what my graph looks like. Okay, now what we need to remember about our graphs are this. Number 1, the gradient of a displacement time graph gives average velocity of the object because we're looking at changing displacement over changing time. You know that. So remember, gradient would be when we take our triangle, that would be my change in S, change in Y, change in time, change in X. You know that from maths. You know that gradient, I'm just going to remind you here quickly, is change in Y over change in X. Change in Y happens to be S. Change in X happens to be T. That means the gradient of this graph gives me V. Gives me velocity. The area under a velocity time graph, now you know this from GCSE, gives me displacement. The area, if I take this, would be time times height. Okay? You know, this is a rectangle. Times height. V times T. V times T is our displacement. Okay, v times t is displacement. There you go, v times t. Okay, that's nice and easy. The gradient is acceleration. Here, that gradient happens to be 0 because there's no change in velocity. So that means that our gradient is 0, acceleration is 0. Gradient, change in y over change in x, change in y, change in x, gives us acceleration. If we now constant positive acceleration, what we need to remember is that means it's getting faster. We're going to cover bigger amounts of distance in the same time interval. Velocity increases constantly at the same rate. Acceleration is now not going to be 0, but it means, and if our velocity is getting bigger, we generally say acceleration is positive. As you can see, the rate, this graph is curving. It's getting a bigger curve. This means finding the gradient is a little more difficult. So what happens here, so I'm just going to take that away, is we would need to find the gradient by finding the tangent at different points in the graph. And different tangents will give us a different value. We would then be able to plot those values onto a graph. That graph will give me a nice straight line like this, okay? And that is because it's accelerating, it's getting faster and faster and faster. I said to you in the last, just now, that the gradient, so the gradient of my graph would give me my acceleration, and that's going to be a value. So that acceleration is going to actually have a value that we can use, okay? From an acceleration time graph, if we took the area under the graph, we would be able to get velocity at a specific time period. So if I took that, say, at 5 seconds, whatever this time is, times by that value, that would give me the velocity at that point in time, because we would then have acceleration is velocity time divided by time. So if I went acceleration times time, I get velocity. Okay? So if we had to look at an example, because it sometimes makes it easier, for an object that moves from rest with an acceleration of 10 meters per second squared, using equations of motion, I can actually get values for this, and the scales moved a little bit on this, which happens. So that's 5, that's 1 is there, 2 is there. Let's just fix this, 3, 4, and 5. And that ends at 5, okay? And I would use equations of motion, the Suvat equations, to calculate these values in order to get to these graphs. Doing it this way, it is actually easier to plot the graphs. You will have to know how to plot these graphs. So you will be given exercises, and you need to know how to do them, as everything graphing is very important. As you can see from this graph, the longer time goes on, the steeper the graph gets. If I wanted to know what the velocity, if I was given the displacement time graph, and I said to find the velocity at a specific point, say 4 seconds, I would need to draw a tangent on my graph and work out the gradient of the tangent. And remember, you always use a sharp pencil, nice big gradient triangle. Please don't make it too small. Use as much of your graph as possible. And the thing with the tangent is it really must touch your graph only at that one point, if at all possible. You want it to touch your curve as little as possible. It's a skill. It's one you need to practice. So my tangent gives me the velocity and at a specific time period, and it's still the gradient of the graph at that point. The area under this graph still gives me displacement. I know now I have a triangle, that doesn't matter. The half is just a constant, because remember, you would go a half times base times height. It will still give you the displacement of my object. The gradient of this graph still gives me acceleration. It doesn't matter that it looks different to the last one. And now, if I had to take the area under the graph for the full 5 seconds, and that would be 5 times 10, that's 50. That 50 is what we know is as fast as it's going after 5 seconds. If I wanted it after 4 seconds, I would go 4 times 10. It's 2 seconds, 2 times 10. So it's the area under the graph at that specific point in time for the acceleration to find the velocity. Okay? So, when we have a negative acceleration, the difference now is that the distances get smaller. Those distances get smaller because your velocity is getting smaller. The smaller the velocity, the slower it's moving. The slower it's moving, the less distance it's going to travel. Acceleration becomes negative because there must be a force acting against the object like brakes, which is in the negative direction. That negative direction means the acceleration is negative. Negative acceleration has to slow it down. So, my graph, again, is a curve for displacement time. That curve, however, now shows me that every time I take a tangent, the tangent's gradient gets smaller and smaller. Okay? That means it's slowing down. Okay? If I look at it, and here, of course, I'm assuming it would have had to have a velocity before I could do anything with it. It's slowing down, going from a big velocity to a small velocity. Each of these gradients, if I work them out, plotted them on that graph, would give me a nice straight line. That, of course, is if I get those gradients correct. Now, because it's slowing down, acceleration, you can see, you know this from maths, that's a negative graph. Okay, that means the acceleration is negative. Acceleration must sit below the line, must sit on the negative part of the line. All of the graphs that I've drawn, barring the acceleration one, I've drawn above. So displacement and velocity, I've shown you above the lines as positive values for velocity and displacement. They absolutely can be negative. But the shape is what we're looking at. So you've got to remember, when there's a curve in displacement, it means there's an acceleration of some kind. If this line is straight, it means it's constant acceleration, either forward or backwards, speeding up or slowing down. Also, if it's horizontal, then it means that there's zero acceleration. Okay? Here, my gradient here is zero. That just means that we've got constant acceleration. The acceleration in reality isn't always constant. It's changing, and we will look at those later, not necessarily in graph form, but in other sections of this. Okay,